Good morning, everyone. My name is Kumari Hariprasad, a BTech ECE student from VIT AP University, working with Emertxe Information Technologies. Today, I am excited to present my project, the EV ADAS dashboard. This project combines the power of tiny computer chips with smart software to create real-time tracking safety system for next-generation electric vehicles. Let's dive into our presentation. Before looking at the code, let's ask a simple question. Why do we care? Modern electric cars aren't just mechanical machines anymore. They are computers on wheels. A smart dashboard is crucial because it acts as the bridge between the car's brain and the human driver. It translates the complex sensor data into clear visual signals so the driver can make split second safety decisions over there. And then we have to build this. We designed a neat four-stage system that mirrors a real production electric vehicle, and then we have those stages. Stage 1 consists of our sensors. We use knobs to simulate user controls like the gas, brake pedals, and three ultrasonic sensors to act as the car's eyes. And then, as stage 2 is the brain, that is the STM32 Blue Pill microcontroller. It runs the physics math for the car and processes all the safety rules. And then we have stage 3 is our data highway. It bundles everything into clean messages and streams them every 100 milliseconds using the UART protocol communication. And then we have stage 4 is the beautiful Python display that visualizes the speed, battery status, and an interactive bird eye view of the surrounding roads. These are all our four-stage development process, and we have all 9 phases of our project visual on our slide. And then I'm going to explain those 9 stages. Bringing a complex system like this to life requires a structured plan. We broke our projects into 9 clear step by step phases. We started by setting up our coding environment, then we configured the hardware pins, programmed the EV driving map, built the smart ADAS safety sensors, added emergency alarms, and finally created the visual dashboard. This structured approach ensured that every single layer of the car system works smoothly together. And then let's look at how the car actually drives in the first few phases. We set up our internal timers to handle tasks at different speeds. For example, the car's engine calculations update every 10 milliseconds, while the sensors looks for obstacles every 100 milliseconds. We create a realistic driving model that handles speeds up to 200 kilometers per hour, mimics a 20 kilowatt hour battery, and even features regenerative braking, meaning the battery recharges slightly whenever you press the brake pedal. Here, our innovation is there. We can also generate our power whenever we brake, and our battery will be charged. And then we have, now let's talk about the magic feature, the ADAS safety engine. First, we have forward collision warning. If a car ahead is less than 50 centimeters away, the system calculates the time left before impact and sound can alarm. Second, we have blind spot detection. When you are driving fast, if an obstacle sneaks upon your left or a right side with the 30 centimeters, a warning light immediately alerts you. We even added a parking score to help you park safely when driving under 10 km per hour. And then safety means being prepared when things go wrong. Our system features an intelligent fault handler. If the motor overheats above 90 degrees or the battery drops below 2%, the car instantly switches into a fault state, cuts all motor power to the zero, launches a warning light on. All of these telemetry data is packed into an organized live text message stream that changes colors based on the priority: green for normal, amber for warning, and red for critical dangers. And we have UART shell and Python dashboard. To tie it all together, we created two power software tools. The first is the UART shell, when acts like a diagnostic terminal. It allows us to safely type text commands, to inject fake faults or drain the battery to see how the car reacts. The second tool is our beautiful Python dashboard. It runs smoothly at 90 frames per second, giving the driver a gorgeous analog speedometer, a live battery bar, a rolling history chart of the speed, and the bird's eye view of nearby obstacles. And we have vehicle state machine and end-to-end workflow visual. To keep everything organized, the car operates using a structured state machine. The vehicle always knows exactly what it is doing. It starts is parked, press the gas pedal, that means acceleration pedal slightly, and it goes to ready. Push it further and you are in driving mode. Hit the brakes and it is switches to the regenerating mode to save energy. And as you can see from the center lines, if a critical emergency happens at any point, the system overrides everything and jumps straight to the fault mode to save the lives of the driver, and it's for safety reasons. And we have result and demo session. I will show how I executed everything and all. I will keep maintain everything. And here you can see our real world testing results. On the left, our speedometer responds instantly to users input. You can watch the battery drain during heavy accelerations. On the right, you can see our blind spot monitoring in action. The amber warning light symbol triggers perfectly on when an obstacle is close by, and we added smart filtering to ensure there are zero false alarm or annoying flickering lights for driver. And then this is here we have also what happens. I want to say something. What happened during extreme emergencies means when a front obstacle blocks the car, the entire dashboard flashes bright red with a critical alarm warning. Below that, you can see our over temperature fault testing. The moment our sensors hit 90 degrees, the motor torque instantly dropped to zero to prevent an engine fire. At the right is our command terminal showing that all of our hardware signals match our software displays perfectly. And then in conclusion, this project successfully bridges the gap between affordable embedded hardware and advanced life-saving software. It shows exactly how the cars of tomorrow can keep drives safer through smart automation. Thank you so much for this time and attention. Before I am going to conclude my presentation. I want to show how I built and executed my project. I have opened everything. First of all, we have large code, right? Here we created a full project file. EV dash, we have everything under this. We have header files over here and we have source files over here. First we have ADAS header file which I am going to open. Here we created everything of header files and we also created a source file for it. We will call those functions which are created in header file of ADAS and we will be going to call over this so that we will get the, and this here is EV. We have fault managing is here, fault, and its source is over here. You can see everything. I will be give you the link in description as well. You can get the codes over here. We also have your shell. Maybe error is there. I will going to execute it. I will gonna build project. You can see zero errors and zero warning I got. That means I will before going to I have to generate a binary file, right? For that I will generate a binary file. I will go to settings, not this one, maybe I will click on main, properties, settings. Where is my settings? This is not, I think I have to build it once again. Build project. Properties, maybe. Here you can see I am selecting the convert to binary. I am showing to you. Apply and save. Once again you build your project means it will generate your binary file and it will be saved over there. This is a software called STM32F103C8T6 We had used I coded everything over here. Coding part and simulation part is done here, and for it is an online based test, so that we can't have hardware. For that we used PICSimLab for our hardware integration. You can see over here I used an STM32 microcontroller, which will be helpful for everywhere. I will load my binary file, which is generated by STM32F103C8T6 I'm generated. It will be closed and open. It is a virtual terminal I built. You can see I'm getting all the values: speed, SOC, torque, temperature, and all will be getting every 10 milliseconds. This will be updated over here. These, and then we have spare parts like this. Uh, if we are hardware means we can give that, but um I didn't have hardware, that's why I built hardware components also in a software called PICSimLab. This pedal is for my speed pedal, acceleration pedal, which is a speed, and this is for my brake purpose. These are all potentiometers. These four are potentiometers which I use to calculate acceleration, brake, SOC, and motor temperature. State of charge and motor temperature. Sorry for the disturbance. Okay, let's go to our project. These are all input, giving inputs and all. And then we have here LEDs. This is collision front. If there is any collision between our front vehicle and our vehicle, this red light will be happen. This is blind spots left and right. If there is any vehicle coming too much close to our object, our vehicle, then these alarms will trigger. And this is a motor temperature. If you can see over here, if motor temperature rises too much, this alarm will be triggered. And then we have front, if front distance collision will occur, alarms will, like that only we have left, and like that only we have right. And this is buzzer. Okay, I will go to my Python dashboard, which I executed through my command prompt. You can see I downloaded Python required software and then I executed it. You can see this is my dashboard. Here you can see speed, SOC, battery life is there, and you can see torque, acceleration, brake pedal, motor temperature, alarm is there, fault numbers are given. The different faults is there, right? So fault signal is on, whether getting data or not we have, and then I will minimize this to understand better, and I will give this is over here. Maybe all are not visible, right? Okay. Okay, now you get to know. Now I am going to increase my motor temperature. It will take some time. You can see here is the motor temperature too high and fault is showing here. Fault is detected, and it will, according to that, it will go ahead. I'm increasing my SOC. And then we will check for front collision. You can clearly see there is a front collision. It is critical. Alarm is going ahead, and there is an issue. Like that, we given our software is built just before you seen right every coding part. Over there, we given fault and alarms, everything right. Over there, we will create it and everything. And when we come here is 90-meter distance is there. That's why it's not gonna bring an alarm. Everything you can see. It will take some time because we are simulating everything in software, right? And here also greater than 50 centimeters. That's why it's also not gonna be alarm. If I go to much lesser, you can see alarm is detecting BSD right. You can clearly see. And if I gonna bring it to left, alarm also generating. This is all our output and presentation. One more thing, we used an VSC tool for generating a virtual pair between the COM1 and COM6. I will show you. I used it for Python dashboard COM6, and my PICSimLab is simulated with COM1. Sorry, here I will show you which COM is given to. You can clearly see COM1 is given. Here COM2 and we given the getting repeated. I will close this, and this also I will close. Here I have to open. I will open this. Sorry for the delay. You have seen right, I simulated everything. Oh, I will maximize it and I will set. I will set this. You can see everything is getting blind spot left, right one. We have motor temperature alarms, and then if I increase the brake pedal, you can see brake is increased over here. There's a slight issue with my speedometer. So okay, I will debug it. This is my simulation. As I shown everything that I built and I executed. First of all, I will thankful to Emertxe for giving this great opportunity. Uh, in Emertxe, I got this internship opportunity, UART internship opportunity, and there I learned a lot from classes. The ma'am helped me more. She built everything. She explains it's very nice. You seeing right? This all we built only with the guidance of Emertxe, and once again I thank you for Emertxe for giving this opportunity. And I will gonna conclude. Okay, no problem. I learned these all embedded things over here which helped me a lot, and we built something great. Slight network issue is there. Okay. Sorry. Where is my presentation? Here it is. Okay. Thank you for watching this video. This is my presentation of EV dashboard. Once again, I'm thank you to Emertxe for giving this opportunity. Thank you. Thank you all.